The universe is a place of unimaginable beauty and wonder, but it is also home to some of the most terrifying and dangerous objects imaginable. Hidden in the vastness of space are forces and phenomena that defy our understanding, where the very laws of physics seem to stretch and break. From black holes that trap everything within their grasp, to stars that explode in violent supernovae, to enigmatic bursts of radiation that could wipe out entire worlds in an instant, these cosmic giants represent the most extreme and destructive powers in existence. Yet within this chaos, there is also a strange balance. These deadly forces are not only the harbingers of destruction, but also the creators of galaxies, stars, planets, and even life itself. What happens when two supermassive black holes collide? How can a neutron star, no larger than a city, contain the mass of our Sun and send out beams of deadly radiation across the cosmos? And could a hidden blazar, its jets aimed directly at Earth, unleash a stream of high-energy particles capable of sterilizing entire regions of space? This journey through the universe's most dangerous objects will explore these questions and more, taking us from the explosive birth of new elements in supernova to the mysterious and mind-bending possibility of white holes, the time-reversing twins of black holes. Join me as we explore the most dangerous objects in the universe. Stellar mass. Black holes in binary systems. The hidden predators. Stellar mass. Black holes are some of the most mysterious and dangerous objects in the universe. While supermassive black holes, found in the centers of galaxies, tend to dominate the conversation, there is another kind that often goes unnoticed, yet could be lurking much closer to us. These are stellar mass black holes. They are born from the collapse of massive stars, and they are far more common than their supermassive counterparts. What's more unnerving is that many of these stellar mass black holes live in binary star systems, orbiting alongside another star, quietly waiting for their chance to strike. In a binary system, one of the two stars evolves faster, reaching the end of its life. If it's massive enough, the star collapses into a black hole, becoming an invisible predator in the system. The surviving star continues to shine, unaware that its companion has transformed into something far more dangerous. This is the hidden nature of stellar mass black holes. They often don't reveal themselves. Unlike normal stars, they don't emit light on their own. They are cloaked in darkness, and unless they're feeding on material from their companion, they can be almost impossible to detect. Imagine a scenario where one of these black holes starts to feed on its partner star. Slowly, over time, the gravitational pull of the black hole draws in gas and material from the companion star, creating a swirling disk of matter around the black hole. This process generates intense radiation, often in the form of X-rays, which can be detected by telescopes. The sight of a star losing its outer layers to a hungry black hole is both fascinating and horrifying. The black hole can devour its partner over millions of years, turning what was once a harmonious stellar duo into a deadly feeding ground. The terrifying reality of stellar mass black holes lies in their stealth. Since they don't emit light unless they're actively consuming material, many of them remain hidden. They could be floating through space, entirely undetectable until they begin their meal. This raises the unsettling possibility that one of these black holes could be much closer to Earth than we realize. It's estimated that there could be thousands of stellar mass black holes scattered throughout our galaxy, each one potentially part of a binary system. These hidden predators are not just consuming their companions. In some cases, as they devour material from the companion star, they can also emit powerful jets of energy. These jets, made up of high-energy particles, can travel vast distances through space. While the idea of a black hole's jet reaching Earth is unlikely, it's not outside the realm of possibility. If a stellar mass black hole were to be close enough, the radiation from these jets could cause significant damage, disrupting satellites and other space-based technology, or even posing a threat to life on Earth. What makes these black holes even more dangerous is that we might not see them coming. They could be drifting through the galaxy, quietly orbiting another star, until some change triggers them to start feeding. Once that happens, the process could escalate quickly, leading to the black hole unleashing a torrent of energy that could have catastrophic consequences. By the time we detect the warning signs, intense X-rays, or perhaps the appearance of a jet of radiation, it could be too late to do anything about it. One of the most concerning aspects of stellar mass black holes is how close some of them could be to us. On the cosmic scale, distances are measured in light years, and our galaxy is a vast expanse of stars, planets, and other objects. However, it's possible that one of these dangerous binary systems is hiding in what we would consider our galactic backyard. Within just a few thousand light years, there could be a stellar mass black hole slowly siphoning off material from its companion, undetected by us. Given how difficult it is to spot these black holes unless they're actively feeding, it's not beyond reason to think that one could be relatively close without our knowledge. The technology we use to search for stellar mass black holes relies on detecting the effects they have on their surroundings. When a black hole is pulling in matter from a companion star, the material heats up as it spirals inward, producing X-rays that we can pick up with space-based telescopes. But not all black holes are actively consuming their partners, meaning many could be invisible to us. They are like cosmic landmines, scattered throughout our galaxy, waiting for the right conditions to reveal themselves. For now, we rely on surveys of the sky to search for signs of these dangerous objects. Astronomers are constantly on the lookout for unusual X-ray sources, which could indicate the presence of a black hole feeding on its companion star. But it's a difficult task. The universe is vast, and our ability to detect these hidden predators is limited by our technology. Even with all the advancements in telescopes and space observatories, we are still only scratching the surface when it comes to understanding the full extent of the dangers posed by stellar mass black holes. It's a chilling thought. As we go about our daily lives on Earth, there could be a black hole, just a few thousand light-years away, quietly waiting for its chance to consume. There's no way of knowing for sure just how many of these hidden killers are out there, but their potential for destruction is immense. In the grand scheme of things, stellar mass black holes may be smaller than the supermassive black holes at the centers of galaxies, but their ability to wreak havoc on their surroundings is no less terrifying. We are still learning about these stellar mass black holes and the threat they pose. As our technology improves, and we continue to explore the far reaches of our galaxy, we may uncover more of these hidden predators. The question is, will we find them before it's too late? Or are they already too close for comfort? As the hunt for these black holes continues, we are reminded of the incredible dangers that lurk in the universe. Dangers that may be much closer to home than we ever imagined. FMY Bubbles, the galactic bombshells, stretching tens of thousands of light-years above and below the center of our galaxy, the FMY Bubbles are one of the most striking and mysterious structures ever discovered in the Milky Way. These gigantic bubbles of high-energy radiation, first detected by NASA's Fermi Gamma Ray Space Telescope, reveal a glimpse of the turbulent past of our galaxy. While they don't pose an immediate threat, their presence raises questions about the history of the Milky Way and whether such violent events could happen again. The FMY Bubbles, with their vast size and energy, seem to point to a time when the center of the Milky Way was far more active than it is today. At the heart of our galaxy lies a supermassive black hole called Sagittarius A, a behemoth weighing about 4 million times the mass of the Sun. Today, this black hole is relatively quiet, though it still exerts a powerful influence on the stars and material in its immediate surroundings. But the FMY Bubbles suggest that at some point in the past, Sagittarius A may have unleashed a burst of energy so powerful that it blew massive amounts of radiation into space. These bubbles span about 25,000 light-years in both directions, extending above and below the plane of the galaxy. The radiation within them is intense, consisting of gamma rays, which are the most energetic form of light. Such energy levels indicate that whatever caused these bubbles was an extraordinarily powerful event, and one that left an enduring mark on our galaxy. But the true nature of this event remains a cosmic mystery. There are several theories about how the FMY Bubbles formed, and the most widely accepted one involves the supermassive black hole at the center of the galaxy. According to this theory, Sagittarius A may have gone through a phase of intense activity in the distant past, possibly consuming large amounts of gas and dust. When a black hole feeds, the material doesn't simply vanish into the event horizon. Instead, some of it can get flung outward in powerful jets of energy, and it's possible that one or more of these jets created the Fermi bubbles. These outbursts would have been strong enough to push gamma rays and other high-energy particles far out into space, creating the massive structures we see today. Another possibility is that the bubbles formed as a result of star formation near the galactic center. The core of the Milky Way is home to some of the most energetic processes in the galaxy, including the rapid formation of stars. When massive stars reach the end of their lives, they can explode as supernovae, releasing huge amounts of energy. It's possible that a burst of star formation, combined with supernova explosions, contributed to the creation of the Fermi bubbles. While the exact cause of the Fermi bubbles is still unknown, one thing is clear. They are a sign that the center of our galaxy has not always been the calm, quiet place it appears to be today. Instead, it has experienced periods of extreme violence, with outbursts of energy powerful enough to shape the very structure of the galaxy. And these outbursts could happen again. The idea that the Milky Way's central black hole might erupt in the future is a sobering thought. While Sagittarius A is relatively quiet now, black holes can be unpredictable. If the black hole were to start consuming a large amount of material, it could trigger another outburst, potentially sending gamma rays and other high-energy particles across the galaxy. In such a scenario, the radiation could pose a serious threat to anything in its path, including Earth. Fortunately, the Earth is located about 25,000 light-years away from the galactic center, which provides a measure of protection. However, radiation from such an event could still disrupt satellites, power grids, and other critical systems. It's unlikely that such an event would occur in the near future, but the Fermi bubbles remind us that our galaxy is not as stable or predictable as we might like to believe. What makes the Fermi bubbles even more intriguing is that they seem to be a relatively recent phenomenon in cosmic terms. The bubbles are estimated to be only a few million years old, which is quite young when you consider the age of the galaxy, which is around 13.6 billion years. This suggests that the event or series of events that created the bubbles occurred long after the formation of the Milky Way, perhaps as recently as when the ancestors of early humans were beginning to walk the Earth. The fact that such a dramatic event happened so recently on a cosmic scale raises questions about whether the Fermi bubbles are part of a regular cycle of outbursts from the galactic center. Could we be living in a period of relative calm between these explosive episodes? If so, when might the next outburst occur? These are questions that astronomers are actively trying to answer. But for now, we are left to wonder what the future holds for our galaxy and its supermassive black hole. One of the challenges in studying the Fermi bubbles is that they are so large and diffuse, making it difficult to gather detailed information about their origins. Gamma rays, unlike visible light, are challenging to detect and require specialized instruments like the Fermi Gamma Ray Space Telescope. Even with the data we have, scientists are still working to piece together the full story of how these bubbles formed and what they tell us about the history and future of the Milky Way. Wolf-Rayet stars, galactic fireballs waiting to explode. Wolf-Rayet stars are some of the most extreme and dangerous stars in the universe. These massive, highly unstable stars are nearing the end of their lives, and their final act could be one of the most violent and destructive events the universe has to offer. Unlike many stars, which fade away gradually, Wolf-Rayet stars burn brightly, furiously shedding their outer layers of gas at incredible speeds. This constant shedding creates powerful stellar winds, pushing material away from the star at hundreds of kilometers per second. They are among the hottest stars known, with surface temperatures reaching tens of thousands of degrees Celsius, far hotter than our own sun. But it's not just their intense heat or winds that make Wolf-Rayet stars so dangerous, it's what happens next. These stars are essentially ticking time bombs, waiting to explode. When they finally do, the resulting supernova could release an enormous amount of energy into space. For stars as massive and unstable as Wolf-Rayet stars, this explosion might not just be an ordinary supernova, it could produce one of the universe's most deadly phenomena, a gamma-ray burst. Gamma-ray bursts are incredibly intense, focused beams of gamma radiation that shoot out from the poles of a dying star during certain types of supernovae. They are among the most powerful explosions known, capable of releasing more energy in a matter of seconds than our Sun will emit over its entire lifetime. If the poles of a Wolf-Rayet star are aligned just right, a gamma-ray burst could be aimed directly at Earth, sending a beam of lethal radiation across the vastness of space. The consequences would be devastating. If a gamma-ray burst from a nearby Wolf-Rayet star were to hit Earth, the effects could be catastrophic. While the burst would only last for a few seconds or minutes, the radiation it releases could strip away our planet's protective ozone layer, exposing life on the surface to harmful ultraviolet radiation from the Sun. Without the ozone layer to shield us, life on Earth would be vulnerable to increased radiation, potentially leading to mass extinctions. The atmosphere could also be severely damaged, altering weather patterns and disrupting ecosystems. The full impact of such an event is difficult to predict, but it's clear that it would be a disaster on a global scale. Fortunately, gamma-ray bursts are relatively rare, and the odds of one being aimed directly at Earth are low. But that doesn't mean we're entirely safe. Astronomers have identified several Wolf-Rayet stars in our galaxy, and while none are thought to pose an immediate threat, their presence is a reminder that the universe is full of dangers we don't fully understand. One of the most famous Wolf-Rayet stars is WR-104, located about 8,000 light-years from Earth. This star is part of a binary system where it is slowly orbiting another star. WR-104 is shedding its outer layers, creating a spiraling plume of gas that surrounds the system like a cosmic pinwheel. What makes WR-104 particularly interesting and potentially dangerous is that it appears to be aligned in such a way that, if it were to go supernova, one of the poles could be pointed directly at Earth. If this alignment is correct, it raises the possibility that any gamma-ray burst from WR-104 could be aimed in our direction. Scientists are still studying the star to better understand its orientation and how likely it is to pose a threat, but the fact that it's even a possibility shows just how dangerous these stars can be. The sheer size and volatility of Wolf-Rayet stars are what make them so dangerous. These stars are typically 20 times more massive than the Sun, and their immense gravitational pull causes them to burn through their nuclear fuel at an incredibly fast rate. This leads to extreme instability, with the outer layers of the star being blown away in all directions. Over time, the star sheds so much mass that only its hot, dense core remains. This core will eventually collapse under its own gravity, triggering the supernova explosion that ends the star's life. But before that final explosion, Wolf-Rayet stars put on a dramatic show. Their stellar winds create enormous clouds of gas and dust, which can stretch out for hundreds of thousands of kilometers. As the star continues to lose mass, it becomes surrounded by a glowing, turbulent shell of material. This process of mass loss makes Wolf-Rayet stars some of the brightest objects in the sky, visible even from great distances. Their powerful radiation can light up the surrounding gas, creating nebulae that glow with an eerie, otherworldly beauty. Despite their stunning appearance, Wolf-Rayet stars are a reminder of the violent processes that shape the universe. They are the precursors to supernovae, the explosions that create the heavy elements needed for planets, stars, and even life itself. Without the explosive deaths of massive stars like Wolf-Rayet stars, the universe would lack many of the elements that make up the world around us. In this way, the death of these stars is both destructive and creative, forging new materials in the fires of their explosions. While the universe needs stars like these to create new elements, their instability makes them some of the most dangerous objects in space. The exact timing of a Wolf-Rayet star's explosion is difficult to predict. Some could explode tomorrow, while others might burn for millions of years before reaching the end of their lives. This unpredictability adds an extra layer of mystery to these stars. We know they will explode. We just don't know when. Astronomers continue to study Wolf-Rayet stars, searching for signs that might help us better predict when one of these stars is about to go supernova. Advances in technology have allowed us to monitor stars more closely, measuring the rate at which they are losing mass and studying the behavior of their stellar winds. But even with all of this information, we are still largely in the dark when it comes to predicting the exact moment of their demise. One thing is certain: when a Wolf-Rayet star finally explodes, the result will be one of the most spectacular and violent events in the universe. These stars have lived fast and burned brightly, but their fiery deaths will leave a lasting impact on the galaxy. For now, they remain cosmic time bombs, waiting for their moment to erupt. Their fate is sealed, and when the time comes, their final act will be one of unparalleled destruction. Wolf-Rayet stars are a testament to the incredible forces at work in the universe. They are both creators and destroyers, responsible for forging new elements and reshaping the galaxy with their explosive deaths. Yet their volatility and potential to unleash gamma-ray bursts make them objects of awe and fear. As we look to the stars, we can't help but wonder which of these galactic fireballs will be the next to explode. And when it does, what will be the consequences for the rest of the universe, including us? The answers may lie hidden in the distant future, but the danger is ever present, reminding us of the delicate balance between creation and destruction in the cosmos. The Great Attractor, the hidden colossus. Deep in the distant reaches of space lies one of the most mysterious and puzzling objects ever discovered, the Great Attractor. It is a gravitational anomaly so powerful that it is pulling entire galaxies, including our own Milky Way, toward it at astonishing speeds. The exact nature of the Great Attractor remains largely unknown, hidden in a region of the sky obscured by our own galaxy. The immense pull it exerts, however, is undeniable, dragging us and everything around us in its direction, creating one of the most perplexing mysteries in modern astronomy. What makes the Great Attractor so elusive is its location. It's situated in what astronomers call the zone of avoidance, a region of space that's almost impossible to observe directly because the dense stars and dust of the Milky Way's galactic core block our view. This obstruction makes it incredibly difficult to study the Great Attractor with optical telescopes, leaving much of its nature hidden from view. Despite this, scientists have detected its influence using other means, such as radio waves and X-rays, which can penetrate through the dust and gas. What we do know is that the Great Attractor exerts a tremendous gravitational force, affecting a large portion of the universe around it. It's as if an invisible hand is reaching out across the cosmos, pulling galaxies, clusters of galaxies, and everything in between toward it at speeds of millions of miles per hour. Our own galaxy, along with the entire local group of galaxies, is moving toward this mysterious region of space, drawn in by a force we barely understand. The enormity of the Great Attractor's gravitational pull suggests that whatever lies there is colossal in size and mass, far beyond anything we can see or imagine. One of the most pressing questions about the Great Attractor is what exactly it is. Some theories suggest that it could be a massive supercluster of galaxies, a vast collection of thousands or even millions of galaxies, all bound together by gravity. Superclusters are some of the largest structures in the universe, and it's possible that the Great Attractor is one of these structures, pulling in galaxies from all directions. Another possibility is that the Great Attractor could be hiding an enormous black hole at its center, a black hole so massive that it is pulling entire galaxies toward it. Black holes are known for their ability to warp space and time, and if a supermassive black hole exists in the heart of the Great Attractor, it could explain the immense gravitational pull that we observe. But there's also the chance that the Great Attractor is something entirely new, something that challenges our current understanding of how the universe works. The universe is vast and still holds many secrets, and the Great Attractor could be a clue to some deeper, more fundamental truth about the nature of reality. It's a tantalizing mystery, one that has sparked endless debate among scientists and astronomers. While we may not know exactly what the Great Attractor is, we do know that we are moving toward it, along with countless other galaxies. The Milky Way is currently hurtling toward the Great Attractor at a speed of roughly 600 kilometers per second, a speed that's hard to comprehend on a human scale. We are part of a vast cosmic migration, drawn inexorably toward this hidden colossus. But what will happen when we get there? Will our galaxy, along with others, eventually collide with whatever massive structure lies at the heart of the Great Attractor, or will we simply be absorbed into its gravitational pull, lost in the vastness of space? The future of our galaxy, and indeed the future of the entire region of the universe around us, could be shaped by the Great Attractor. One possibility is that over the course of billions of years, galaxies will continue to move toward the Great Attractor, eventually leading to massive collisions between galaxies. When galaxies collide, their stars don't typically smash into one another because the distances between stars are so great. Instead, the gravitational forces of the merging galaxies pull them into new shapes, forming vast elliptical galaxies, while the gas and dust within them can trigger bursts of star formation. These cosmic collisions are dramatic, reshaping the galaxies involved and creating new generations of stars. But the Great Attractor is more than just a destination for colliding galaxies. Its immense gravitational pull could be part of a larger pattern that stretches far beyond even the boundaries of the visible universe. Some scientists believe that the Great Attractor may be connected to an even larger structure known as the Shapley supercluster, a region of space that contains the largest known concentration of galaxies in the nearby universe. The Shapley supercluster could be the true cause of the gravitational pull we observe, with the Great Attractor being just one part of a larger, interconnected cosmic web. Even though the Great Attractor seems far beyond our reach, it still raises important questions about our place in the universe. We are part of a vast, interconnected network of galaxies, all influenced by forces we don't fully understand. The discovery of the Great Attractor reminds us that we are not static, but in constant motion, drawn towards some unknown future. It also serves as a reminder of the immense scale of the universe and how much of it remains hidden from our view. As our technology improves, astronomers are continuing to study the Great Attractor, hoping to unravel its secrets. Advances in radio and X-ray astronomy have allowed scientists to peer through the zone of avoidance, revealing glimpses of the galaxies and structures hidden there. In time, we may come to better understand what the Great Attractor is and how it fits into the larger picture of the universe. For now, though, it remains a cosmic enigma, a lurking colossus whose pull we cannot escape. One of the most unsettling aspects of the Great Attractor is that we don't know how it will affect our galaxy in the long term. While it's unlikely that we'll see the full consequences of our journey toward the Great Attractor for billions of years, the fact that we are being drawn toward such an immense gravitational force raises important questions about the future of the Milky Way. Will our galaxy be torn apart by the gravitational pull of the Great Attractor, or will we merge with other galaxies in a cosmic dance that reshapes the universe? These are questions that we may not be able to answer in our lifetimes, but they remind us of the dynamic and ever-changing nature of the universe. Black dwarf stars, the cold remains of stellar death. In the far distant future of the universe, long after the last stars have flickered out and the skies have gone dark, what will remain? Scientists believe that one of the final remnants of stellar life will be black dwarf stars. These cold, dark objects represent the last stage of a star's life cycle, a stage that no star has yet reached, but one that will eventually come to define the future of the cosmos. Black dwarfs are theorized to form from white dwarfs, the dense remnants left behind after a star has exhausted all of its nuclear fuel and shed its outer layers. Today, white dwarfs are still hot, glowing objects, slowly cooling as they radiate away the last of their heat into space. This cooling process takes an incredibly long time, trillions of years. But eventually, white dwarfs will cool to the point where they no longer emit any detectable light or heat. When this happens, they will become black dwarfs, cold and dark, blending into the backdrop of the universe. It's a stage of stellar evolution that we haven't yet observed because the universe simply hasn't existed long enough for any white dwarfs to cool that much. But in the far future, the universe will be filled with these stellar corpses drifting silently in the void. The idea of black dwarfs is both fascinating and eerie. They would be completely dark, making them almost impossible to detect. Without light, they would no longer shine in the night sky, and their temperatures would have dropped to near absolute zero, the coldest possible state of matter. A black dwarf would be nothing more than a slowly cooling ball of degenerate matter, no longer capable of supporting any kind of nuclear fusion. These remnants would no longer interact with their surroundings in any significant way, becoming ghostly relics of a once vibrant universe. Black dwarfs represent not just the end of individual stars, but the distant, inevitable future of the universe itself. As time marches on, all stars, no matter how large or small, will eventually run out of fuel and die. For smaller stars like our Sun, this means they will end their lives as white dwarfs. Over the course of trillions of years, these white dwarfs will cool and fade into black dwarfs. The universe, once filled with the brilliant light of billions of stars, will eventually be populated by these cold, dark objects. In this future scenario, any planets that might still exist around black dwarfs would be cold, lifeless worlds. Without the warmth and energy of a star, these planets would have no way of sustaining life. If there were any civilizations or living beings left by this time, an unlikely prospect, they would have to adapt to a universe without light or heat. The cosmic glow of distant stars, which has illuminated the universe for billions of years, will fade away, leaving behind only the cold, black remnants of what once was. This long, slow cooling process reflects the ultimate fate of the universe. Eventually, the universe will reach a state known as heat death, where all thermodynamic activity has ceased, and no usable energy remains. Black dwarfs are a key part of this future, as they are among the last objects to remain after all other forms of energy have been exhausted. In this frozen, dark universe, the formation of new stars will no longer be possible. Galaxies will drift apart, and the space between them will expand into an empty void. Without the light of stars, the universe will grow colder and darker, entering a state of eternal stillness. What's haunting about this scenario is the idea of time continuing on, but without any activity, any movement, or any light. The black dwarfs, once brilliant stars in their own right, will simply drift through this darkness, silent and inert. They will be scattered across the universe, each one isolated in the vast emptiness of space. The galaxies that once held these stars will have long since dispersed, their constituent parts stretched out across the universe by the relentless force of cosmic expansion. The black dwarfs will no longer feel the pull of gravity from nearby stars or planets because there will be nothing nearby to interact with. They will simply float in the cold darkness, forgotten remnants of a time when the universe was alive with light. The formation of black dwarfs is part of a much larger story about the evolution of the universe. From the Big Bang, when the universe was hot, dense, and filled with energy, to the birth of the first stars and galaxies, the universe has been in a constant state of change, but this change is leading to an eventual end. As stars burn through their fuel and galaxies drift farther apart, the universe is slowly winding down. The formation of black dwarfs marks one of the final stages of this process, as the last remnants of stellar activity finally fade away. In the far, far future, the universe may reach a point where only black dwarfs remain. With no stars left to give light, no supernovae to release energy, and no planets to harbor life, the universe will be a cold, quiet place. It's difficult to imagine such a future, as it's so different from the universe we know today, full of vibrant stars and galaxies. But this future is what scientists believe will eventually come to pass, based on our current understanding of physics and cosmology. The ultimate fate of black dwarfs is another mystery. Some scientists speculate that, over an unimaginably long period of time, even black dwarfs might disintegrate. One possibility is that they could slowly decay through a process called quantum tunneling, where particles within the black dwarf escape, causing it to gradually dissolve. If this happens, the black dwarfs will eventually disappear entirely, leaving nothing behind. Others believe that black dwarfs might persist indefinitely, remaining as the last relics of a universe that has grown cold and dark. Whatever their fate, black dwarfs represent the final chapter in the life of stars and the evolution of the universe. They are a chilling reminder of the impermanence of even the most powerful and enduring objects in the cosmos. Today, we live in a universe filled with light, but the time will come when that light is gone, and all that remains are cold, dark objects drifting in the vast emptiness of space. Thornzit Cow Objects, the strange stellar hybrids. Among the strange and mysterious objects in the universe, few are as unusual as Thornzit Cow Objects, TZOs. These rare stellar hybrids are born from a highly improbable and dramatic cosmic event. When a neutron star, one of the densest objects in the universe, is swallowed by a red supergiant, a massive star that has reached the late stages of its life. The result is a bizarre combination where the dense core of the neutron star sits inside the bloated outer layers of the supergiant. This creates a star that operates under completely different physical conditions from any normal star. To understand just how strange Thornzit Cow objects are, it's important to consider the two components that make them up. A neutron star is the remnant left behind after a massive star explodes in a supernova. These stars are so dense that a single teaspoon of neutron star material would weigh billions of tons on Earth. Their gravitational pull is incredibly strong, and they can spin rapidly, emitting intense magnetic fields and beams of radiation. Red supergiants, on the other hand, are enormous stars that are nearing the end of their lives. These stars have expanded to many times their original size, their outer layers puffed out into space as they burn through the last of their nuclear fuel. In a Thornzit Cow object, these two vastly different stars combine. The neutron star, after being ejected from its original supernova, crashes into the red supergiant. Instead of being destroyed, the neutron star sinks into the core of the supergiant, where it becomes the new center of the hybrid star. This is a situation unlike anything seen in normal stellar evolution. The outer layers of the red supergiant continue to operate as they normally would, fusing elements in nuclear reactions. But the presence of the neutron star inside changes everything. The physics of a Thornzit Cow object are completely different from those of a typical star. The core, instead of being made of hot, dense gas undergoing fusion, is now a super-dense neutron star. This leads to some unusual effects. For one, the immense gravitational pull of the neutron star could cause the outer layers of the red supergiant to behave unpredictably. In a normal red supergiant, the outer layers are relatively stable, but in a TZO they may be subject to sudden and violent shifts. The neutron star's presence could trigger outbursts or flares, sending material flying into space at high speeds. These eruptions could be unpredictable and dangerous, especially for anything nearby. If such an object existed close to our solar system, its unpredictable behavior could pose a significant threat. A massive outburst from a Thornzit Cow object could release intense radiation or cause shock waves to ripple through space. Depending on how close it was, the effects could be felt here on Earth, potentially disrupting satellites, communications, and even causing damage to our atmosphere. The magnetic fields around a TZO could also be extremely powerful, further adding to the dangers for any nearby systems. In addition to these outbursts, the presence of a neutron star inside the red supergiant could create unusual gravitational and magnetic effects. Neutron stars already have some of the strongest magnetic fields in the universe, and when combined with the massive outer layers of a red supergiant, these fields could behave in ways we don't fully understand. The hybrid star could act like a giant magnet, with intense magnetic fields stretching out across space. These fields could interact with any nearby stars or planets, possibly affecting their magnetic environments. The gravitational pull of the neutron star, combined with the mass of the red supergiant, could also warp space in unpredictable ways. What makes Thornzit Cow objects even more mysterious is how rare they are thought to be. So far, only one possible candidate for a TZO has been observed, a star known as HV 2112, located in the Small Magellanic Cloud, a nearby galaxy. Even this detection is uncertain, and scientists are still debating whether HV 2112 is truly a Thornzit Cow object. This rarity only adds to their mystique. The conditions required for the formation of a TZO are incredibly specific, and it's likely that these objects only form under very rare circumstances. A neutron star must survive its supernova and then encounter a red supergiant in just the right way for the merger to occur. Despite their rarity, the existence of Thornzit Cow objects shows us just how diverse and strange the universe can be. Stars are typically thought of as massive balls of hot gas, burning brightly for millions or billions of years before eventually burning out or exploding. But TZOs remind us that stellar evolution can take strange and unexpected turns. The combination of a neutron star and a red supergiant is a cosmic oddity, one that doesn't fit neatly into our normal understanding of how stars live and die. The possible instability of Thornzit Cow objects is another reminder of how unpredictable the universe can be. Stars are not always the steady, unchanging objects we sometimes imagine them to be. They can undergo sudden and violent transformations, especially when unusual circumstances like the merger of a neutron star and a red supergiant come into play. This instability could make TZOs some of the most dangerous objects in space, especially if they exist in regions where other stars or planets are nearby. The future of a Thornzit Cow object is another area of uncertainty. Given the strange nature of these stars, it's unclear how long they can last in their hybrid state. Some scientists believe that TZOs may eventually collapse, with the neutron star triggering a supernova-like explosion. If this happens, the hybrid star could blow apart, sending vast amounts of material into space. Such an explosion would be similar to a traditional supernova, but with the added twist of the neutron star's involvement, which could lead to even more extreme outcomes. The explosion could release high-energy radiation, shock waves, and other dangerous effects, potentially affecting a wide area of space around it. The presence of a neutron star at the heart of a TZO also raises questions about what happens after the outer layers of the red supergiant are lost. Over time, red supergiants lose mass through strong stellar winds, shedding their outer layers into space. If the neutron star remains stable, it's possible that a Thornzit Cow object could eventually strip away its outer layers, leaving behind only the neutron star and a cloud of material. Alternatively, the neutron star could destabilize and trigger a final catastrophic event, destroying the entire star. Supermassive black hole mergers, the ultimate collision. Some of the most extraordinary and violent events happen when entire galaxies collide. These cosmic crashes are slow, drawn-out processes that take millions or even billions of years to unfold. And at the heart of many galaxies lies something even more dramatic: a supermassive black hole. When two galaxies merge, their central supermassive black holes are drawn toward each other, and eventually they collide. The result is one of the most powerful and awe-inspiring events in the universe: a supermassive black hole merger. These mergers are not just collisions of unimaginable size, they are also the source of immense energy, capable of sending ripples through the very fabric of space-time. When two black holes finally meet and merge, the energy released in the form of gravitational waves spreads out across the cosmos, traveling through space at the speed of light. These waves were first detected by scientists in 2015, a breakthrough that allowed us to observe black hole mergers for the first time, though on a smaller scale than supermassive black holes. Still, the collision of two supermassive black holes is on a level beyond anything we've yet detected, a cosmic event that reshapes the surrounding galaxy. Supermassive black holes are staggering in their size and power. They can have masses millions or even billions of times greater than that of our Sun, and their gravitational pull is so strong that not even light can escape. When two of these giants collide, the energy released is almost unimaginable. As the black holes spiral toward each other, they create powerful gravitational waves, disturbances in space-time that ripple outwards like waves on the surface of a pond. These waves carry with them the signature of the merger, allowing scientists to detect them from Earth using instruments like LIGO and Virgo, which are sensitive enough to pick up these faint ripples from millions of light-years away. The collision itself is a slow-motion disaster on an incomprehensible scale. As the two black holes get closer, their immense gravity begins to warp space-time around them. Time slows down near the event horizon, and the stars, gas, and dust in their vicinity are caught up in a gravitational tug-of-war. The two black holes gradually spiral inward, pulling everything nearby along with them. Eventually, they meet in a cataclysmic collision, merging into a single, larger black hole. The energy of this merger is converted into gravitational waves that spread across the universe, and the newly formed black hole is left to settle into its new state, having absorbed the mass and energy of both its predecessors. For any planet or star systems unfortunate enough to be near a supermassive black hole merger, the effects could be devastating. The sheer force of the gravitational waves could distort space-time itself, causing stars and planets to shift in their orbits. If Earth were close enough to a merger, the resulting gravitational forces could wreak havoc on our solar system, potentially disrupting the delicate balance that keeps the planets in their stable orbits around the Sun. In extreme cases, entire star systems could be torn apart by the immense gravitational pull of the merging black holes, flinging planets into space or pulling them into the event horizon where they would be consumed by the growing black hole. Fortunately, our galaxy is not currently on a collision course with another galaxy, and our own supermassive black hole, Sagittarius A, is relatively quiet. However, in the distant future, the Milky Way is expected to collide with the Andromeda Galaxy, an event that will likely lead to the merger of their central black holes. This merger won't happen for another 4 to 5 billion years, but when it does, it will be one of the most spectacular events in the history of the universe. For any beings that might still be around to witness it, the collision would be a sight unlike anything ever seen before, as the two galaxies slowly merge into one and their black holes spiral toward each other in a slow but inevitable cosmic dance. Watching such a merger up close would be both terrifying and awe-inspiring. The collision of two supermassive black holes is an event that defies human understanding of scale and power. The sky might be filled with bright bursts of light as gas and stars are pulled into the accretion disks around the black holes, lighting up the surrounding space in a fiery display. The gravitational forces involved would warp the very fabric of space, stretching and distorting everything nearby. For any observer, the view would be both beautiful and unsettling, a reminder of the incredible forces at play in the universe. But for all its beauty, a supermassive black hole merger could also signal the end of a galaxy as we know it. The forces involved in the collision could disrupt the structure of the galaxy, sending stars and planets careening into new orbits, or even flinging them out of the galaxy entirely. The gravitational waves generated by the merger would propagate across the universe, stretching and compressing space as they pass through it. These waves could be detected billions of light years away, offering scientists on Earth a glimpse into the most powerful events the universe has to offer. The aftermath of a supermassive black hole merger would be equally dramatic. The newly formed black hole, now even more massive than before, would dominate the center of the galaxy, its immense gravity shaping the orbits of the stars around it. Any gas or dust left in the vicinity could be drawn into the black hole's accretion disk, where it would heat up and emit powerful X-rays as it spiraled inward, before eventually being consumed. The merger would also likely trigger bursts of star formation, as the gravitational interactions between the two galaxies compress gas clouds, causing them to collapse and form new stars. Over time, the galaxy would settle into a new shape, having been transformed by the collision of its two black holes. While supermassive black hole mergers are incredibly rare on human timescales, they are happening somewhere in the universe right now. The vastness of space means that many of these events are taking place far beyond our ability to detect them. But as our technology improves, we may one day be able to observe these mergers in greater detail. The discovery of gravitational waves has already opened up a new window into the universe, allowing us to detect the unseen forces at play in these collisions. As we continue to study these waves, we will gain a deeper understanding of how black holes merge and what happens when two of the most powerful objects in the universe collide. In the grand scheme of things, supermassive black hole mergers are a natural part of the evolution of galaxies. As galaxies move through the universe, they sometimes collide and merge with one another, and when they do, their central black holes eventually meet in a final catastrophic event. These mergers shape the structure of galaxies, influencing the formation of stars and planets and helping to drive the evolution of the universe. They are among the most violent and powerful events we know of, and they remind us of the immense forces at work in the cosmos. For now, the supermassive black holes in our galaxy and Andromeda remain on their slow path toward eventual collision. It's a process that will take billions of years, and by the time it happens, the universe will be a very different place. But when the time comes, the merger of these two black holes will be an event of unimaginable power, sending ripples through space-time and reshaping the galaxy. It will be the ultimate collision, a moment when the most powerful forces in the universe come together in a final, cataclysmic event. White dwarf. Supernovae, cosmic time bombs. White dwarfs are the quiet remnants of stars that have burned through their nuclear fuel and collapsed. But unlike more massive stars that end their lives in dramatic supernovae or collapse into neutron stars and black holes, white dwarfs are typically stable, slowly cooling and fading into the background of the universe. Yet under the right circumstances, even these faint, dim stars can become some of the most powerful cosmic time bombs in the universe. When a white dwarf exists in a binary system with a companion star, it can gradually siphon material from its partner. This process can go on quietly for millennia, unnoticed by the universe at large, until one day the white dwarf suddenly reaches a critical mass and explodes in a spectacular Type Ia supernova, releasing more energy in a few moments than the Sun will produce over its entire lifetime. These Type Ia supernovae are unique because they result from the explosion of a white dwarf rather than the collapse of a massive star. The process begins when the white dwarf, which is made mostly of carbon and oxygen, pulls in material from a nearby star in its orbit. Over time, this steady flow of material increases the white dwarf's mass. But there's a limit to how much mass a white dwarf can accumulate before it becomes unstable. This limit, known as the Chandrasekhar limit, is about 1.4 times the mass of our Sun. Once the white dwarf approaches this critical mass, the pressure at its core becomes so intense that it triggers a runaway nuclear reaction, causing the entire star to explode in an instant. What makes Type Ia supernovae particularly dangerous is that they can happen without warning. A white dwarf could be quietly feeding on its companion for thousands or even millions of years, completely undetected, before suddenly igniting. There are no signs or early indicators of an imminent explosion, which makes them subtle yet deadly threats. In contrast to massive stars, which show signs of instability or swelling before their final collapse, white dwarfs remain relatively stable right up until the moment of detonation. This makes them some of the universe's most silent killers, capable of erupting into a massive explosion without giving any clues that such a disaster is about to occur. The power of a white dwarf supernova is staggering. These explosions can outshine entire galaxies for a short period of time, producing a burst of light and energy that can be seen across vast distances. During the explosion, the white dwarf is completely destroyed, with its material ejected into space at speeds of up to 3,000 kilometers per second. The intense radiation from the supernova can have devastating effects on anything nearby. Planets within the system, if they exist, would be completely obliterated, and the shock waves from the explosion would travel outwards, sweeping away any remaining gas and dust. But the effects of a white dwarf supernova are not confined to just the immediate surroundings. The radiation released during the explosion, particularly in the form of gamma rays and X-rays, can travel vast distances, potentially affecting planets and stars far beyond the binary system. If a Type Ia supernova occurred within a few thousand light-years of Earth, the radiation could have serious consequences for our planet. While the explosion itself wouldn't directly harm Earth from that distance, the intense radiation could interact with our atmosphere, damaging the ozone layer and exposing the surface to dangerous levels of ultraviolet radiation from the Sun. The disruption of Earth's atmosphere in the wake of such an event could lead to a cascade of environmental effects. Increased ultraviolet radiation could damage the DNA of living organisms, leading to higher rates of mutations and potentially causing widespread extinctions. The climate could also be affected, as the radiation could alter the chemical composition of the atmosphere, potentially leading to changes in temperature and weather patterns. While it's unlikely that a supernova could completely wipe out life on Earth from a few thousand light-years away, the fallout from such an event could still be devastating, particularly for ecosystems and species that are sensitive to changes in radiation levels. Because white dwarf supernovae are relatively common in the universe, astronomers have long been interested in studying them. Not only are they important for understanding stellar evolution, but they also play a crucial role in helping scientists measure the expansion of the universe. Type Ia supernovae are known as standard candles, meaning that their brightness is predictable based on their distance. This allows astronomers to use them to measure distances to galaxies and track the expansion rate of the universe over time. The discovery that the universe is expanding at an accelerating rate, a finding that led to the theory of dark energy, was based in part on observations of type Ia supernovae. Despite their scientific importance, the unpredictable nature of these explosions makes them a potential threat. While there are no known white dwarf systems close enough to Earth that could produce a supernova in the near future, the possibility remains. It's difficult to predict when and where the next type Ia supernova will occur, as the process that leads to the explosion can take millions of years. But because these supernovae are relatively common in our galaxy, occurring about once every few hundred years, it's likely that one will happen again in the not-too-distant future. When a white dwarf finally reaches the point of explosion, the resulting supernova is a breathtaking display of nature's power. The outer layers of the star are blasted into space, while the core is completely destroyed. The energy released in the explosion can temporarily rival the combined light of billions of stars, lighting up the night sky and leaving behind a glowing cloud of gas and dust that expands over time. These remnants, known as supernova remnants, can persist for thousands of years, slowly fading as they disperse into the interstellar medium. The aftermath of a Type Ia supernova can also have far-reaching effects on its environment. The material ejected from the explosion is rich in heavy elements like iron and nickel, which are created during the final moments of the white dwarf's life. These elements are then scattered into space, where they can eventually become part of new stars, planets, and even living organisms. In this way, white dwarf supernovae play a critical role in enriching the universe with the building blocks of life. But while these explosions are essential for the evolution of galaxies and the creation of new stars and planets, they also serve as a reminder of the inherent dangers present in the universe. The fact that a relatively quiet, unassuming star like a white dwarf can suddenly become a cosmic bomb highlights the unpredictability of the cosmos. And though we may be safe for now, the possibility of a nearby supernova in the future is a real and unsettling one. Fast radio bursts, FRBs, the universe's mysterious signals. In the vast reaches of space, astronomers have detected some of the most intense and brief flashes of radio energy ever observed, known as fast radio bursts or FRBs. These bursts of radio waves, lasting only a few milliseconds, release more energy in that tiny moment than the sun produces in an entire day. Despite their brief duration, the power packed into an FRB is staggering, suggesting that whatever causes them must be an incredibly energetic event. But the most intriguing aspect of FRBs is that their origins remain largely unknown, making them one of the greatest unsolved mysteries in modern astronomy. What makes FRBs so terrifying, in a sense, is the sheer energy they carry. In a fraction of a second, these bursts release the same amount of energy that our sun emits in a full 24-hour period. To generate such immense energy in such a short time, the events behind these bursts must be extraordinary, far more powerful than anything we have observed in our immediate cosmic neighborhood. This raises unsettling questions about what kinds of cataclysmic forces might be responsible for these bursts. Are they the result of exploding stars, or are they tied to something even more extreme, like the collision of black holes or neutron stars? The energy involved suggests that whatever is causing FRBs has the potential to destroy anything nearby. Since their discovery in 2007, FRBs have puzzled scientists. The signals are not just rare, they are also unpredictable. They appear suddenly from seemingly random locations in the sky, making it difficult for astronomers to pinpoint their exact sources. Unlike many other cosmic phenomena that can be studied over time, FRBs vanish almost as soon as they are detected, leaving little more than a brief signal to analyze. And yet, despite these challenges, astronomers have recorded hundreds of FRBs over the years, each one adding to the mystery of their origins. There are several theories about what could be producing these powerful bursts. One possibility is that FRBs are linked to neutron stars, specifically a type of neutron star called a magnetar. Magnetars have extremely strong magnetic fields, trillions of times stronger than Earth's magnetic field, and they are capable of releasing enormous amounts of energy when their magnetic fields shift or crack. This could result in a sudden burst of radio waves, potentially explaining the power and brevity of an FRB. However, not all FRBs fit neatly into this explanation, and other possible causes continue to be explored. Some scientists have speculated that FRBs might be the result of black hole activity, such as when two black holes merge. These mergers release gravitational waves, which we can now detect, but they could also produce powerful bursts of electromagnetic radiation, including radio waves. If FRBs are connected to such events, it would mean that they are linked to some of the most violent and destructive forces in the universe. The collision of two black holes warps space-time itself and releases a tremendous amount of energy. If this energy includes an FRB, it would provide a clue about the types of catastrophic events that produce these signals. There is also the possibility that FRBs could be tied to the collapse of stars into black holes. When a massive star runs out of fuel, its core can collapse into a black hole, while the outer layers are ejected in a supernova explosion. This sudden collapse could generate a burst of radio waves that might match the characteristics of an FRB. The short duration and high energy output of such an event could explain why these bursts are so intense and why they appear so briefly before disappearing. But not all FRBs may come from violent events. A more speculative and perhaps unsettling possibility is that FRBs are artificial in nature, created by advanced civilizations. Some scientists have entertained the idea that FRBs could be signals from distant alien technologies, perhaps the result of powerful radio transmissions or energy sources used by these civilizations. While this idea remains purely theoretical, the mysterious nature of FRBs leaves room for speculation. If an advanced civilization were attempting to communicate across the vast distances of space, an FRB might be an effective way to send out a signal. These bursts are detectable across billions of light years, and their intensity could allow them to stand out against the cosmic background noise. The idea that FRBs could be artificial in origin is both fascinating and unsettling. If these bursts are indeed signals from another civilization, what are they trying to communicate? Are these bursts intentional messages or the byproduct of some advanced technology that we cannot yet understand? And if FRBs are artificial, what does that say about the nature of the civilizations producing them? Are they far more advanced than we are, and what might their intentions be? While there is no concrete evidence to suggest that FRBs are anything other than natural phenomena, the possibility lingers in the back of the mind. Even without invoking the possibility of alien civilizations, the unpredictability of FRBs is unsettling. They appear at random, often from distant galaxies, and vanish almost as soon as they are detected. We don't know when or where the next FRB will appear, and each new detection raises more questions than it answers. Some FRBs seem to repeat, occurring multiple times from the same source, while others appear only once, never to be detected again. This inconsistency adds to the mystery as scientists struggle to understand whether all FRBs are produced by the same kind of event or if they have different origins entirely. What would happen if an FRB occurred closer to Earth? While most FRBs detected so far have come from distant galaxies, the energy released in one of these bursts is so immense that even a nearby FRB could have serious consequences. The radiation from an FRB could interact with Earth's atmosphere, potentially disrupting communications or causing damage to satellites. In extreme cases, a particularly strong FRB could pose a threat to life on Earth by stripping away parts of the ozone layer or triggering changes in the climate. As scientists continue to study FRBs, the hope is that by detecting more of these bursts, patterns will emerge that can help unravel their origins. Advances in radio astronomy have already allowed for the detection of more FRBs than ever before, and with new telescopes coming online, the number of detected bursts is expected to grow. Each new FRB provides another piece of the puzzle, helping to narrow down the possibilities and bring us closer to understanding what these bursts are and where they come from. The discovery of FRBs has opened up a new frontier in the study of the universe. These mysterious signals, brief but powerful, challenge our understanding of how energy is released on a cosmic scale. Whether they are the result of natural processes, like collapsing stars or merging black holes, or something more exotic like advanced alien technology, FRBs remind us of how much we still have to learn about the universe. Their unpredictable nature and immense energy are a testament to the power and mystery of the cosmos, and they leave us with the unsettling possibility that there are forces at work in the universe that we do not yet understand. The Oort cloud, a distant sea of icy hazards. Far beyond the planets of our solar system, in the cold, dark reaches of space, lies one of the most mysterious and potentially dangerous regions we know of, the Oort cloud. Unlike the familiar orbits of planets and asteroids within our solar system, the Oort cloud is a vast spherical shell of icy bodies that stretches out to nearly a light year from the Sun, extending well beyond the orbit of Pluto. It's not a single object, but a massive collection of billions, if not trillions, of icy remnants from the early solar system, a distant and frozen sea of potential hazards that could pose a serious threat to life on Earth. The Oort cloud itself has never been observed directly. It's so far away and its objects so small and faint that even our most powerful telescopes can't detect them. But scientists are confident that it exists based on the trajectories of long-period comets, those that enter the inner solar system from great distances, only to return to the farthest reaches of space after their brief visits near the Sun. These comets often have orbits that suggest they come from a distant icy reservoir, and the Oort cloud is believed to be the source of these rare but sometimes deadly visitors. The sheer size of the Oort cloud is difficult to comprehend. It is thought to begin around 2,000 to 5,000 times farther from the Sun than Earth is, and it extends out to about 1,000 astronomical units, AU, or about a quarter of the distance to the nearest star, Proxima Centauri. This vast spherical shell surrounds the entire solar system, and it contains countless icy bodies ranging in size from small boulders to comets that could be tens of kilometers across. These objects are remnants of the early solar system left over from the formation of the planets, and they have remained in this distant region for billions of years, barely influenced by the gravitational pull of the Sun. The danger posed by the Oort cloud comes from its unpredictability. While most of its icy inhabitants remain in stable orbits far from the Sun, occasionally they are disturbed. These disturbances can be caused by a variety of factors, such as the gravitational influence of passing stars, the motion of the Milky Way galaxy itself, or even the slight tug of interstellar objects passing near the solar system. When this happens, some of the icy bodies in the Oort cloud can be knocked out of their distant orbits and sent hurtling toward the inner solar system. When a comet from the Oort cloud is disturbed and begins its journey toward the Sun, it can take millions of years to reach us. These long-period comets are different from the shorter-period comets that we are more familiar with, like Halley's Comet, which orbits the Sun every 76 years. Oort cloud comets may only visit the inner solar system once before being flung back into the depths of space, or they may be captured into new orbits that bring them closer to the Sun more frequently. But the most worrying aspect of these comets is their size and speed. Many of them are large enough to cause catastrophic damage if they were to collide with Earth. The most famous example of an impact from a celestial object is the asteroid that struck Earth 66 million years ago, wiping out the dinosaurs and causing massive global devastation. While that object is believed to have come from the asteroid belt between Mars and Jupiter, an Oort cloud comet could cause similar if not greater destruction. Because these comets often travel at higher speeds than asteroids, up to 70 kilometers per second, the energy released in an impact would be enormous, potentially triggering widespread extinctions and altering the climate on a global scale. Unlike near-Earth asteroids, which astronomers are actively tracking, Oort cloud comets are far more difficult to predict. They come from such great distances that we often don't see them until they are well on their way toward the Sun, and by then there may be little time to react. While some comets are detected years in advance, giving us time to study their trajectories, others could approach more suddenly, providing only months or even weeks of warning. This unpredictability makes Oort cloud comets one of the greatest natural threats to life on Earth. In addition to their potential for destruction, Oort cloud comets also offer valuable scientific opportunities. These icy bodies are among the oldest and most primitive objects in the solar system, having remained largely unchanged since the time of its formation. Studying them could provide insights into the early history of the solar system, helping scientists understand how planets formed and how the building blocks of life may have been delivered to Earth. In fact, some scientists believe that comets may have played a key role in bringing water and organic molecules to the early Earth, setting the stage for the development of life. But despite the scientific value of studying comets, the danger they pose cannot be ignored. An impact from a large Oort cloud comet could trigger devastating effects similar to or even greater than the asteroid that wiped out the dinosaurs. The force of such an impact would create a massive crater, releasing vast amounts of dust and debris into the atmosphere. This debris could block out sunlight for months or even years, leading to a nuclear winter scenario where temperatures plummet and global ecosystems collapse. The impact itself would cause widespread destruction, with shockwaves, tsunamis, and wildfires ravaging the planet. Efforts to detect and track comets from the Oort cloud are ongoing, but the sheer size and distance of this region make it a daunting task. Advances in technology, such as the development of more powerful telescopes and space-based observatories, may help scientists better monitor the outer reaches of the solar system in the future. But for now, our ability to predict and defend against an incoming comet from the Oort cloud remains limited. One of the challenges in dealing with the threat of Oort cloud comets is that, unlike asteroids, these comets often have highly elongated orbits that bring them close to the Sun only once in a very long time. This makes them difficult to observe or track over extended periods, and their trajectories can be influenced by a wide range of factors. The gravitational pull of planets, the Sun, and even other stars can alter a comet's path, making it hard to predict exactly where and when it will arrive. Some scientists have proposed ways to defend against an incoming comet, such as using nuclear explosives or kinetic impactors to deflect the object away from Earth. However, these techniques are still largely theoretical, and there is no guarantee that they would work on a large, fast-moving comet from the Oort cloud. Additionally, the short warning time for many of these comets makes it difficult to mount a coordinated defense. Despite the dangers, the Oort cloud remains one of the most mysterious and fascinating regions of the solar system. It represents the outermost boundary of the Sun's gravitational influence, a distant and frozen frontier filled with the remnants of the solar system's formation. These icy bodies, while posing a potential threat, are also relics from a time long before the Earth existed, offering a glimpse into the processes that shape the planets and the Sun itself. Planck stars, the collapsed ghosts of the universe. In the universe, some of the most perplexing and theoretical ideas challenge the boundaries of our understanding of space and time. One such idea is the concept of Planck stars. These hypothetical objects, if they exist, represent a dramatic departure from our conventional understanding of black holes and the collapse of matter under extreme gravitational forces. While black holes are known for the singularities they contain, regions where gravity becomes infinite and the laws of physics break down, Planck stars offer a different, potentially less destructive outcome when a star collapses. At their core, these objects would be incredibly dense, but they may avoid the formation of a singularity by reaching a state where quantum effects of gravity become significant, a state known as Planck density. The idea of a Planck star is rooted in the intersection of quantum mechanics and general relativity, two areas of physics that traditionally don't play well together. General relativity describes how gravity works on a large scale, governing the motion of planets, stars, and galaxies, while quantum mechanics deals with the tiny particles that make up the fabric of the universe. In most cases, these two frameworks function separately. However, in extreme conditions, such as when matter collapses under the intense gravity of a black hole, these two realms must somehow converge. A Planck star is thought to be the result of such a convergence, where quantum gravity effects prevent a complete collapse into a singularity. What makes Planck stars so intriguing and so potentially dangerous is their extreme compactness. If a black hole can collapse to a singularity, its gravity becomes inescapable beyond a certain boundary, known as the event horizon. But in the case of a Planck star, the collapse would be halted before reaching this infinitely dense state. Instead, the object would compress to an incredibly dense but finite size. A Planck star would still exert an enormous gravitational pull, but without the infinite density and strange physics associated with a singularity. In theory, this could make Planck stars more stable than black holes, but their immense gravitational influence would make them no less threatening to their surroundings. One of the most unsettling aspects of Planck stars is that they could be extremely difficult to detect. Unlike traditional black holes, which emit radiation at their boundaries through processes like Hawking radiation or via the accretion of nearby matter, Planck stars might not produce much radiation at all. This means that a Planck star could be wandering through the universe, undetected and unnoticed until it suddenly exerts its gravitational pull on nearby objects. If a Planck star were to pass through a solar system, the gravitational forces it exerts could be catastrophic. Planets might be pulled from their orbits, moons torn apart, and stars disturbed from their stable positions. The unpredictability of such an event is what makes Planck stars such a dangerous theoretical possibility. While black holes are typically found at the centers of galaxies or as remnants of massive stars, Planck stars, if they exist, could form under different circumstances. Their creation might involve more subtle quantum effects that don't follow the same predictable path as black hole formation. This means that Planck stars could exist in places where we don't expect them, possibly wandering through the galaxy like invisible wrecking balls. The idea of a Planck star introduces a new layer of complexity to our understanding of gravity and the nature of collapsed objects. Traditional black holes form when a massive star exhausts its nuclear fuel and collapses under its own gravity, eventually creating a singularity where the laws of physics break down. But with a Planck star, the collapse halts before reaching this extreme state, resulting in a hyperdense object that remains governed by quantum mechanics. In this scenario, the Planck star would still have immense gravity, but without the infinite compression associated with a singularity. This raises profound questions about the nature of space, time, and matter at the smallest and largest scales. At the heart of the Planck star concept lies the idea of quantum gravity, a theory that scientists are still trying to fully understand. Quantum gravity is the theoretical framework that would describe how gravity works on the quantum level, combining the insights of quantum mechanics with the forces of gravity described by general relativity. The problem is, we don't yet have a complete theory of quantum gravity. Planck stars could be a clue to how such a theory might work, offering insight into what happens when matter is compressed to the limits of our understanding. The existence of Planck stars could also mean that the universe holds far more variety in terms of collapsed objects than we currently realize. While black holes have dominated the conversation for decades, Planck stars could represent an entirely different class of objects that form under slightly different conditions. These ultra-dense objects could be out there in the universe, influencing their surroundings in ways that are difficult to detect, but no less dangerous. The potential for Planck stars to disrupt our understanding of physics is profound. If these objects do exist, they challenge the long-held belief that black holes inevitably lead to singularities. Instead, they suggest that quantum effects may provide a natural limit to how much matter can be compressed. This could change the way we think about the life cycles of stars and the ultimate fate of matter in the universe. It could also force us to reconsider the role that quantum mechanics plays in large-scale cosmic events. The discovery of a Planck star would be a revolutionary moment in science, providing direct evidence that quantum gravity is a real and significant force in the universe. Such a discovery could open the door to entirely new branches of physics, allowing scientists to explore the limits of matter and energy in ways we can't currently imagine. But it would also come with its own set of dangers. If Planck stars are as difficult to detect as theorized, their potential to cause destruction on a cosmic scale is a very real concern. A nearby Planck star could exert enough gravitational pull to destabilize entire star systems, potentially wiping out planets and even stars in its vicinity. Blazars, the cosmic death lasers. In the distant reaches of the universe, far beyond our solar system and even beyond the Milky Way, there are objects so powerful and dangerous that they dwarf anything we can imagine. These are blazars, cosmic death lasers powered by supermassive black holes at the centers of distant galaxies. Blazars are a more extreme form of a class of objects known as quasars, which are some of the brightest and most energetic phenomena in the universe. But unlike quasars, whose energy is spread out in different directions, blazars are much more focused. They aim their energy directly at us, sending jets of highly charged particles at nearly the speed of light, like a cosmic laser beam. At the heart of every blazar is a supermassive black hole, millions or even billions of times the mass of the Sun. These black holes are actively feeding, pulling in gas, dust, and other material from the surrounding galaxy. As the material falls toward the black hole, it forms a swirling disk, known as an accretion disk, that heats up to extreme temperatures. This process releases enormous amounts of energy, which can be seen across vast distances. But what makes blazars unique is that the black hole also produces relativistic jets, narrow streams of charged particles that are blasted out from the poles of the black hole at nearly the speed of light. These jets are what make blazars so terrifying. The energy they carry is immense, and because they are so tightly focused, they can travel across millions of light years without losing much of their power. When one of these jets is aimed directly at Earth, it can be detected as an incredibly bright source of radiation, visible across multiple wavelengths, from radio waves to gamma rays. The radiation coming from a blazar is so powerful that it can outshine the entire galaxy that hosts it. But the real danger comes from the fact that these jets are not just light. They are streams of high-energy particles moving at nearly the speed of light, and they can blast through anything in their path. If a relativistic jet from a blazar were to hit Earth directly, the consequences would be devastating. The radiation and high-energy particles in the jet would overwhelm our planet's atmosphere, causing massive damage to the ozone layer and exposing the surface to harmful levels of radiation. This would disrupt communications, satellites, and electronics, but more critically, it would pose a direct threat to life on Earth. The intense radiation could cause widespread biological damage, potentially leading to mass extinctions. In the worst-case scenario, a direct hit from a blazar's jet could sterilize the surface of a planet, wiping out life entirely. One of the most unsettling things about blazars is that we don't fully understand why some black holes generate these jets while others don't. Supermassive black holes are relatively common. Most large galaxies, including the Milky Way, are thought to have one at their center. But only a small fraction of these black holes produce the kinds of focused, relativistic jets seen in blazars. It's not entirely clear what triggers a black hole to become a blazar, or how long these jets last. In some cases, blazars appear to switch on and off over time, with the jets becoming active and then fading away. This raises the unsettling possibility that there could be a supermassive black hole near the Milky Way, quietly waiting to become a blazar and aim its deadly energy in our direction. The power of a blazar comes from the incredible energy released as matter falls into the black hole. When material is pulled toward the event horizon, the point of no return. It is accelerated to nearly the speed of light, causing it to heat up and radiate energy across the electromagnetic spectrum. In some cases, magnetic fields near the black hole can channel some of this material into tightly focused jets that shoot out from the black hole's poles. These jets are made of highly charged particles such as electrons and protons, moving at relativistic speeds. Because the jets are so focused, they can travel vast distances without losing much of their energy, making them visible from billions of light-years away. Blazars are among the most powerful sources of radiation in the universe. They emit energy across the entire electromagnetic spectrum, from low-energy radio waves to high-energy gamma rays. Gamma rays, in particular, are the most energetic form of radiation known, and they can cause serious harm to anything they encounter. A gamma-ray burst from a blazar could penetrate the Earth's atmosphere, causing widespread damage to living organisms by disrupting DNA and causing mutations. The radiation could also trigger chemical reactions in the atmosphere that would deplete the ozone layer, allowing more harmful ultraviolet light from the sun to reach the surface. But while the prospect of a blazar's jet hitting Earth is terrifying, the good news is that the nearest known blazar is millions of light-years away, far beyond the reach of its deadly jets. However, because we don't fully understand what causes a black hole to become a blazar, we can't rule out the possibility that there could be one much closer to us that we haven't yet detected. Supermassive black holes are known to lie dormant for long periods of time, only becoming active when they begin to feed on new material. If a black hole in a nearby galaxy suddenly began to consume a large amount of gas and dust, it could become a blazar, sending its relativistic jets toward Earth. The unpredictability of blazars adds to their terrifying nature. While we have identified several known blazars, it's possible that many more are lurking in distant galaxies, waiting to become active. Because blazars are so bright and energetic, they can be seen across vast distances, but by the time we detect them, the jets may have been active for millions of years. In other words, we could be hit by a jet from a distant blazar long before we have time to respond. One of the most mysterious aspects of blazars is the role that magnetic fields play in generating their jets. It's thought that the magnetic fields around a supermassive black hole can twist and compress as material falls into the accretion disk, creating a kind of cosmic slingshot that accelerates particles to near-light speed. These magnetic fields are incredibly strong, and they help to focus the jets into narrow beams that extend out from the poles of the black hole. But the exact mechanisms behind this process are still not fully understood, and scientists continue to study blazars in the hopes of unlocking their secrets. Blazars also offer a unique window into the behavior of supermassive black holes. Because they are so bright and energetic, they allow scientists to study the environments around black holes in great detail. By observing the light and radiation emitted by a blazar, astronomers can learn about the processes that power these jets and the extreme conditions near the event horizon of a black hole. Blazars provide clues about the nature of black holes, the role of magnetic fields in shaping the universe, and the fundamental forces that govern the behavior of matter and energy. Despite the danger they pose, blazars are a reminder of the incredible power of the universe. These cosmic death lasers, powered by supermassive black holes, represent one of the most extreme and violent phenomena in the cosmos. Their relativistic jets, traveling at nearly the speed of light, are a testament to the immense energy that black holes can generate. Supernovae, stellar explosions that outshine entire galaxies. A supernova is one of the most dramatic and powerful events in the universe. When a massive star reaches the end of its life, it dies in a violent explosion that can briefly outshine entire galaxies. For a few weeks or months, the light from a supernova can be seen across vast distances, marking the final moments of a star that once burned brightly. These explosions are not only spectacular to observe, but they also play a crucial role in the ongoing cycle of creation and destruction in the universe. At its core, a supernova is the death of a star, but it is a death that is anything but quiet. As a star exhausts its nuclear fuel, The delicate balance between the outward pressure generated by fusion reactions and the inward pull of gravity begins to break down. In massive stars, this leads to a catastrophic collapse. The star's core, no longer able to support its own weight, collapses in on itself in a fraction of a second. This collapse generates an enormous amount of energy, causing the outer layers of the star to explode outward in a blast that sends shockwaves through space. The energy released during a supernova is truly staggering. In just a few moments, the explosion can release as much energy as the Sun will emit over its entire 10 billion-year lifetime. This intense burst of energy is what makes a supernova so bright, often outshining all the other stars in its galaxy combined. For a brief period, the dying star becomes one of the most luminous objects in the universe, visible from millions or even billions of light-years away. Supernovae are as deadly as they are beautiful. The radiation produced by the explosion can be lethal to anything in its path. While the majority of supernovae occur far from Earth, the prospect of a nearby supernova is a sobering one. A supernova that occurred within a few dozen light-years of Earth could have devastating effects on our planet. The intense radiation, particularly in the form of gamma rays, could strip away our atmosphere's protective ozone layer, exposing the surface to harmful ultraviolet radiation from the Sun. This would cause widespread ecological damage, potentially leading to mass extinctions, much like the event that is believed to have contributed to the extinction of the dinosaurs. The radiation from a supernova doesn't just impact life on planets, it can also affect entire star systems. A powerful enough explosion can trigger changes in the orbits of nearby planets, disrupt the formation of new stars, and even alter the chemical composition of interstellar space. For stars and planets unlucky enough to be in the vicinity of a supernova, the effects can be catastrophic, with entire systems potentially being destroyed or scattered by the force of the blast. Despite the destructive power of supernovae, they also play a crucial role in the universe's cycle of creation. These stellar explosions are responsible for the creation of many of the heavy elements necessary for life. During the explosion, elements like iron, gold, and uranium are forged in the intense heat and pressure of the collapsing star. These elements are then scattered across space, where they can eventually become part of new stars, planets, and even living organisms. In this way, supernovae are essential to the process of cosmic recycling, breaking down old stars and scattering their remnants to form the building blocks of new ones. This cycle of creation and destruction is one of the most fundamental processes in the universe. Stars are born, live out their lives, and die in explosions that spread their material across the cosmos. The remnants of these explosions, clouds of gas and dust enriched with heavy elements, become the seeds for the next generation of stars. Over billions of years, this process has created the galaxies, stars, and planets that fill the universe today. Without supernovae, the universe as we know it would not exist. There would be no planets, no complex chemistry, and no life. But while supernovae are essential to the formation of the elements that make up planets and living organisms, they also highlight the violent nature of the universe. The same explosions that create the elements necessary for life can also wipe out entire civilizations if they occur too close. In this sense, supernovae are a reminder of the dual nature of the cosmos, where creation and destruction are inextricably linked. The death of a star is not an end, but a new beginning, as the material it leaves behind goes on to form the next generation of stars and planets. One of the most well-known types of supernovae is the Type II supernova, which occurs when a massive star, at least 8 times the mass of the Sun, reaches the end of its life. These stars burn through their nuclear fuel much more quickly than smaller stars like the Sun, and when the fuel is exhausted, their cores collapse, triggering the explosion. In some cases, the core of the star may survive the explosion, collapsing into a neutron star or even a black hole. The outer layers of the star, however, are ejected into space, creating a brilliant explosion that can be seen across vast distances. Type Ia supernovae, on the other hand, occur in a very different way. These supernovae are the result of a white dwarf star in a binary system siphoning material from its companion star. As the white dwarf gains mass, it eventually reaches a critical point where it can no longer support its own weight, causing it to explode in a thermonuclear detonation. Unlike Type II supernovae, which are caused by the collapse of a single massive star, Type Ia supernovae involve the destruction of a much smaller, more compact star. However, both types of supernovae release enormous amounts of energy and are capable of producing the heavy elements necessary for life. The remnants of a supernova explosion can persist for thousands of years. The material ejected during the explosion forms a glowing cloud of gas and dust known as a supernova remnant. These remnants can be incredibly beautiful, lighting up the sky with intricate patterns of glowing material. One of the most famous examples of a supernova remnant is the Crab Nebula, the result of a supernova that was observed by Chinese astronomers in 1054 AD. Today, the Crab Nebula continues to expand, its glowing filaments of gas and dust providing a glimpse of the immense power of the original explosion. Supernovae also play a crucial role in the formation of new stars. The shock waves produced by a supernova explosion can trigger the collapse of nearby clouds of gas and dust, leading to the birth of new stars. In this way, supernovae help to drive the process of star formation, ensuring that the cycle of creation and destruction continues. Without supernovae, the process of star formation would be much slower, and the universe would look very different than it does today. While supernovae are rare events on a human timescale, they are relatively common on a cosmic scale. Astronomers estimate that a supernova occurs about once every 50 years in a galaxy like the Milky Way. Given that there are billions of galaxies in the universe, this means that supernovae are happening all the time, scattering their material across space and driving the ongoing evolution of the cosmos. For all their destructive power, supernovae are a reminder of the delicate balance that exists in the universe. They show us that creation and destruction are two sides of the same coin, with each explosion playing a crucial role in shaping the galaxies, stars, and planets that fill the universe. Without these cataclysmic events, the universe would be a much less dynamic place, with fewer opportunities for the formation of new stars and planets. In this way, supernovae are both a source of destruction and a driver of cosmic creativity, ensuring that the universe remains in a constant state of change and renewal. White holes, the time-reversing twin of black holes. White holes, the theoretical counterparts to black holes, are objects that challenge our understanding of the universe in ways both mysterious and unsettling. While black holes are known for their ability to pull everything toward them, trapping matter, light, and even time itself within their event horizons, white holes represent the exact opposite. Instead of drawing matter in, white holes would expel everything outward, pushing cosmic debris and energy away with overwhelming force. Though none have been observed so far, white holes emerge from the same equations of general relativity that predict black holes, making them a tantalizing, if still theoretical, possibility. In the simplest terms, a white hole is an object where nothing can enter, unlike black holes, which are defined by their inescapable gravitational pull. Once matter crosses a black hole's event horizon, it cannot return. In a white hole, however, everything is forced out. It's a region of space where matter, energy, and radiation are expelled, flung outward into the cosmos. If white holes exist, they would be some of the most violent and chaotic objects in the universe. Their unpredictable bursts of matter and radiation would disrupt anything nearby, turning them into dangerous zones of cosmic upheaval. A white hole's chaotic nature is rooted in the fundamental differences between how it interacts with the universe compared to its black hole twin. Whereas black holes are relatively calm on the outside, invisible until their gravitational effects become noticeable or until they pull in matter, a white hole would be an active, explosive force. It would continually expel material at incredible speeds, creating shockwaves and scattering cosmic debris in all directions. The energy released from a white hole could potentially rival or exceed that of the most violent supernovae, sending radiation and high-energy particles blasting through space. Theoretical physicists who study general relativity suggest that a white hole could be the time-reversed version of a black hole. In other words, while black holes represent a region where time moves forward and matter is trapped, a white hole could represent a situation where time appears to move backward, expelling everything that comes near it. This time reversal property is not just a strange quirk, it raises profound questions about the nature of time itself. Could white holes be places where time runs in reverse, undoing the processes that black holes initiate? This reversal of time is one of the many reasons why white holes challenge our perception of reality. They force us to consider whether time is a fixed and linear concept or whether it can behave in ways we don't fully understand. If white holes are real, they might suggest that time can be manipulated or that it operates differently in various regions of the universe. In this way, white holes introduce a kind of philosophical terror. The idea that time itself can reverse, that processes can be undone as easily as they can be set in motion, throws our very understanding of cause and effect into question. One of the most intriguing ideas surrounding white holes is the possibility that they could be linked to black holes. Some theories suggest that a white hole might represent the final stage of a black hole's life cycle. According to this idea, after a black hole has absorbed matter for billions of years, it could eventually transition into a white hole, ejecting everything it once consumed in a violent burst. If this were true, white holes could serve as the final chapter in the story of a black hole's existence, releasing the matter and energy that had been trapped inside. Alternatively, white holes might be connected to black holes in another, even more profound way. Some speculative theories propose that black holes could serve as gateways to white holes, with matter entering a black hole in one region of the universe only to be expelled by a white hole in another. This concept is tied to the idea of wormholes, tunnels through space-time that connect distant regions of the universe. If black holes and white holes are indeed connected in this way, they might represent a kind of cosmic recycling system, where matter is pulled into a black hole, travels through a wormhole, and is ejected from a white hole somewhere else. Even more mind-bending is the possibility that white holes could be responsible for the creation of new universes. Some scientists have speculated that a white hole might not just expel matter into our universe, but could create an entirely new universe in the process. In this scenario, the singularity at the heart of a black hole, where all the matter and energy that falls in is compressed to an infinitely small point, could give rise to a new universe, with the white hole acting as the Big Bang for this new cosmos. This idea, though highly speculative, raises the possibility that our own universe might have been born from a white hole in some other larger universe, connecting us to a grander multiverse where black holes and white holes act as cosmic gateways between different realities. Despite the many theoretical possibilities, white holes remain purely hypothetical. While black holes have been detected through their gravitational effects and the radiation emitted by the material they consume, no evidence of a white hole has yet been observed. This absence of direct evidence doesn't rule them out entirely, though. It could simply be that white holes are rare, or that they exist in regions of space where they are difficult to detect. If they do exist, they may only appear under very specific conditions, making them elusive and hard to observe with our current technology. Even without direct observation, the idea of white holes forces us to confront some of the most fundamental questions about the universe. They challenge our understanding of how matter, energy, space, and time interact. They also push the boundaries of our imagination, offering a glimpse into a universe where the rules we take for granted, such as the forward flow of time and the inescapability of black holes, might not always apply. The violent expulsion of matter and energy from a white hole would make it an object of immense power and unpredictability. If one were to exist near a star system, the effects could be devastating. The force of the ejected material could disrupt the orbits of planets, potentially pulling them out of their solar systems entirely or flinging them into deep space. The radiation emitted by a white hole could be lethal, sterilizing nearby planets and rendering them uninhabitable. Any star system unfortunate enough to be near a white hole would be subject to a constant barrage of high-energy particles and radiation, making it a chaotic and dangerous environment. If white holes are connected to black holes, they may also represent the ultimate cosmic paradox. Black holes are objects of absolute inescapability, where nothing, not even light, can escape their gravitational pull. White holes, on the other hand, are objects of absolute rejection, where nothing can enter and everything is thrown out. The two represent opposite extremes of cosmic behavior, and yet they may be linked in ways we don't yet fully understand. The mere possibility of white holes adds another layer of mystery to the universe. They remind us that our understanding of space and time is still incomplete, and that the universe may hold secrets far beyond our current grasp. Neutron stars, the dense remnants of catastrophe. Neutron stars are among the most extraordinary objects in the universe, born out of the violent death of massive stars. When a star much larger than the Sun reaches the end of its life, it can explode in a cataclysmic supernova, leaving behind a dense core that collapses under its own gravity. This core becomes a neutron star, an object so dense that a single teaspoon of its matter would weigh more than 1 billion tons. Despite their relatively small size, about 20 kilometers in diameter, roughly the size of a city, neutron stars contain more mass than the Sun, compressed into a volume just a fraction of its size. They are the dense remnants of catastrophe, where the ordinary laws of matter are pushed to their absolute limits. What makes neutron stars so extraordinary is their density. In a neutron star, gravity is so intense that it crushes atoms, forcing protons and electrons to combine into neutrons. This creates an object made almost entirely of neutrons, hence the name. The result is a star where the matter is packed so tightly that a sugar cube-sized piece would weigh more than an entire mountain on Earth. The immense gravitational pull of neutron stars means that anything that comes too close would be pulled in with incredible force, crushed by gravity beyond anything we experience in the normal universe. Neutron stars bend space and time around them, similar to black holes, though without the event horizon that traps everything inside. For all their intense gravity, neutron stars have another feature that makes them even more dangerous: their magnetic fields. A neutron star's magnetic field is trillions of times stronger than Earth's, and this magnetic power can have dramatic effects on its surroundings. Charged particles trapped in the magnetic field are accelerated to near the speed of light, creating beams of radiation that can extend far into space. These beams are sometimes visible as pulsars, neutron stars that spin rapidly and send out regular pulses of electromagnetic radiation, like a cosmic lighthouse sweeping across the universe. Pulsars emit radiation in a precise rhythm, often so regular that their timing can be compared to the most accurate atomic clocks on Earth. Pulsars are not only fascinating objects, but also dangerous ones. The radiation they emit can sterilize any nearby planets, bombarding them with high-energy particles that would obliterate any chance of life. In some cases, these pulses of radiation are powerful enough to be detected across vast distances, hundreds or even thousands of light-years away. The rapid spin of these neutron stars, often rotating hundreds of times per second, creates an intense environment around them, where anything that strays too close would be bathed in deadly radiation. For any star systems unlucky enough to be near an active pulsar, the consequences could be devastating. The extreme rotation speeds of pulsars are one of the unexpected twists in the story of neutron stars. After a neutron star forms, it can continue to spin rapidly due to the conservation of angular momentum from the original star. In some cases, neutron stars spin so fast that they complete a full rotation in just a fraction of a second. These millisecond pulsars can rotate hundreds of times per second, flinging out beams of radiation in regular intervals. This rapid rotation, combined with the star's immense density, makes pulsars some of the most extreme objects in the universe. The forces at play are so intense that they test the limits of physics, offering scientists a unique laboratory for studying the behavior of matter under extreme conditions. One of the most fascinating aspects of neutron stars is what they reveal about the limits of matter. In a neutron star, matter is compressed to unimaginable extremes, far beyond anything that occurs in normal stars or planets. The neutrons in the star are packed so tightly together that they form a kind of neutron soup, where the boundaries between individual particles begin to blur. This leads to the question, is there a limit to how much matter can be compressed? Neutron stars already push matter to the brink, but could there be an even more extreme state of matter where particles are crushed even further? This philosophical curiosity has led some scientists to speculate about the existence of objects even denser than neutron stars. One possibility is the existence of quark stars, objects that would form when the neutrons inside a neutron star are further broken down into their constituent particles, quarks. In a quark star, matter would be compressed to a state where individual neutrons no longer exist, replaced by a sea of quarks, the fundamental building blocks of protons and neutrons. Quark stars, if they exist, would be even smaller and denser than neutron stars, pushing the limits of our understanding of matter to new extremes. Another possibility is the existence of strange stars, hypothetical objects made of strange quarks. Strange stars would be even more exotic than quark stars, consisting of matter that we have never observed in the universe. These objects remain speculative for now, but they highlight the fact that neutron stars may not represent the final word in the story of collapsed matter. The universe could hold even more incomprehensible forms of matter waiting to be discovered. Despite their extreme properties, neutron stars also serve as essential cosmic laboratories. By studying them, scientists can learn more about the fundamental forces of the universe, such as gravity, electromagnetism, and nuclear physics. Neutron stars are one of the only places in the universe where we can observe matter in such an extreme state, offering insights into the behavior of matter under conditions that can't be replicated on Earth. They provide clues about the behavior of particles at densities far beyond anything we experience in the normal universe, helping to push the boundaries of physics. But neutron stars are not just objects of scientific curiosity. They are also reminders of the violent processes that shape the universe. Every neutron star is the remnant of a supernova explosion, a catastrophic event that marks the death of a massive star. These explosions scatter heavy elements like iron and gold across the cosmos, seeding future generations of stars and planets. In this way, neutron stars are not just the remnants of destruction, they are also part of the cycle of creation that drives the evolution of the universe. The heavy elements created in supernovae go on to form new stars and planets, including planets like Earth, where life can emerge. For all their extreme properties, neutron stars are relatively common in the universe. There are thought to be millions of neutron stars in our galaxy alone, though most are difficult to detect because they are small and faint. The ones we do observe, such as pulsars, give us a glimpse into the incredible forces at work inside these objects, but they are just the tip of the iceberg. Many neutron stars are likely drifting through space unnoticed, their intense gravitational pull and magnetic fields hidden from view. In the end, neutron stars are both a scientific curiosity and a reminder of the immense power of the universe. They are the dense remnants of catastrophic explosions where gravity and matter are pushed to their absolute limits. They challenge our understanding of physics, offering a glimpse into a realm where the normal rules of matter break down, and they push us to consider whether there are even more extreme objects waiting to be discovered. Whether they appear as pulsars, emitting regular bursts of deadly radiation, or drift silently through space, neutron stars are a testament to the incredible forces that shape the cosmos, serving as both a reminder of destruction and a symbol of the universe's capacity for renewal. I hope you enjoyed this video. If you did, feel free to subscribe. Thank you for watching.